Okay, thank you very much for the invitation to this meeting. I'm really amazed at the level of expertise brought together in this online conference, and I have to look up some of the talks and the recordings. I'm going to talk today about artificial intelligence analysis of reflectivity data. I choose a catchier title. I'm also doing neural network analysis as the talks before and after me. You also don't need a big computing center like the one shown in the background. All you need is for reflectivity curves your laptop, or if you want to speed it up a little bit, maybe buy a gaming PC. And artificial intelligence is gaining a lot of headlines because of Google and Facebook and Tesla all doing speech recognition things and self-driving cars. And we are using the very same tools, the same PyTorch or TensorFlow frameworks from Facebook and Google. So in some sense, we are doing the artificial intelligence thing, even if we are only in a subgroup of machine learning and or neural networks. This work was started something like 3 years ago, and our first publication is one where Alessandro Greco is the first author, with some other people from the Schreiber group in Tübingen, Vladimir Starostin, Alexander Hinterhofer, Alexander Gerlach. We've built upon this work. Maximilian Skoda is also co-author on the second paper, and I'm continuing this work now that I'm in Graz with David Maricik, Erich Hüttmeier. So I'm going to present a bit of an overview of several papers. So the one published is this Journal of Applied Crystallography paper 2019, and we've got 2 accepted papers to come out soon, or they are already online. And I'll cover a range of topics. My outline is as follows. So I'll give a quick introduction into neural networks, because I'm not sure everyone's familiar. Then I'll show how neural networks can fit our X-ray reflectivity curves. How well does this work? If it's not applicable to experiments, it wouldn't be of any use. In this second paper down here, you can read in more detail where neural networks fail to predict X-ray reflectivity and also neutron reflectivity curves, which may be interesting for not just for understanding the neural networks, but understanding the limits of the techniques in general. Even so, I know that all of you are experts and probably have a good intuition about a lot of these pitfalls. And then I'll talk about 2 unpublished things which we've been working on. So neural network prediction of the error bars of our fit parameters. This is very similar to the previous talk, and I really liked the previous talk and the Fisher information and uncertainty discussion we had. And lastly, I'll make the point that maybe we should not predict real space. So we are very focused on going from reciprocal space to real space. Maybe that's not what we should do in every case. So sometimes people are interested to optimize some material property, or are interested in understanding some kinetics or dynamics of growth or crystal formation. And I'll give an example how we don't go to the real space. We don't care about the real space structure, so to speak, in the first place, but we directly want to extract the growth law with a neural network. So let me give a very quick primer. We've just had in the chat some links to material on the internet. There's tons of very good introductions. Just very briefly, it's modeled after the neuron in our brains, which is the cell here, which receives inputs, some signals, does something with them, and then fires it off the axon to some other neurons. And the individual neuron in an artificial neural network has numbers as inputs, sums up all these inputs, but not just inputs, but the weighted inputs with these weights, W, and then puts it through a nonlinear function and puts out another number. So that's the basic unit of our neural network. So you compute the weighted sum of the inputs X and put it through a nonlinear function G, which is very important. Without this nonlinear function, you would just do matrix multiplication. And this is the individual neuron, and you can then hook them up in several layers behind each other. Here are the inputs, which could be our reflectivity values, the weights, the next layer of neurons, which do the summing and a nonlinear function and so on, the last layer, and this outputs numbers we are interested in. And a neural network can model any nonlinear mapping from a high-dimensional space to another high-dimensional space. So in principle, it can perform the duties of any algorithm. And to give you this very quick example, image recognition is one of the things where neural networks are very good at. So you have maybe a 1 megapixel image, so 1 million numbers, and you want to classify, say, dogs and cats, and you want to have 2 numbers as output. So you need a neural network with 1 million inputs and 2 outputs on the other side. And so you connect all your neurons, you put a couple of layers of neurons in there, and the weights in the beginning, you just put random numbers there and do this calculation. It's a well-defined mathematical calculation of all these functions. And you get some random numbers out here in the back because the weights are random and this is wrong. And now you want to train the neural network. So you need to show it a lot of data. And the data here, in this case, images, also needs labels. So you need to know what you're looking at. You can't just show it unknown stuff without telling it what it is. And with lots of images, I mean, around 1,000 is sort of the minimum, 10,000, 100,000 is better. 1 million is almost certainly enough, depending on how complex the problem is. And then you look at what the neural network predicted and adjust the weights by gradient descent in such a way that the numbers that comes out gets better and better when you show them the images over and over again. And I felt right at home with the neural networks because we in the extra reflectivity community, of course, have all done a lot of fitting. And so fitting the neural network is a little bit similar. So you can have too much variance, too many variables, too small a network, too few parameters. So it's a little bit similar, even so one has to say here we fit maybe 100,000 weights, so a lot more parameters than we do in extra reflectivity. And to me, it's still amazing that this converges to some reasonable things. So now, after this introduction to the neural network, can it fit real curves? So what do? We have our reflectivity, which I certainly do not need to introduce in this audience. And we all know it's easy to calculate fringes given the real space structure, but the inverse problem is hard and ill-defined. So what we do is we do the quick, easy step. We calculate, we simulate 100,000 data sets of different reflectivity curves, and we have the labels from our simulations. Then we start to put the numbers we generated in these reflectivity curves as the input, put a neural network behind here with 400 neurons, 800 neurons, 400, 300, 200, 100. And in the end, we have 4 neurons, which give us 4 numbers of the thickness, roughness, scatter length, density, and the thickness of the oxide layer. So we have a simple one-box model with a little bit of an oxide layer with 1 parameter below. So a fairly simple model, and we see how this performs. And we quite often do in situ real-time experiments where we grow a film. So here on the right, you can see the reflectivity pattern of a growing film. The fringes get narrower and narrower, and the red line is the fit that the neural network draws through this. And it's not always perfect, but in general, it's a pretty good fit. And the Schreiber group is working on a project where things like this could be used maybe as a real-time analysis during a beam time. It certainly is very fast, so you can perform around 30,000 fits per second I think my newer graphics card, this one is a 3-year-old graphics card. Very recent graphics card is maybe 100,000 fits per second. You don't need user input, so we've seen this before, that the starting variables don't need to be well tuned by hand, but the neural network finds within its range where it's been trained, it usually finds a very nice solution. And I want to stress that this is very easy to program, and also the training, if you have some fitting experience, is not terribly complicated. And as an example here, I show the neural network which can be used for the fitting. Before I showed one with a few more layers, but this one will also fit your reflectivity curves. You've got 52 inputs in this case, 52 measured reflectivity values, and then 3 layers of 1024 neurons, and then 4 outputs. And I'm really amazed that with those few lines in Python, with the free TensorFlow and Keras libraries are sufficient to do what we do. So I really enjoy programming neural networks because it's easy. And how does this perform now? If we look a bit in more detail, so here you see some snapshots of this growing film. The fringes get narrower, and the fits look pretty decent. And now if we plot the thickness as a function of time and the roughness as a function of time and the scattering length density, we have plotted here a manual fit in blue, and the green line is a neural network prediction, and in general, they match up pretty well. Maybe sometimes the neural network is a little bit more noisy, but some of the noise is also probably in the manual fit, so we don't have the perfect label. And if we make this comparison quantitative, and by this I mean that we looked at here 5 growth runs of molecule DIP at different temperatures, molecule copper phthalocyanine and sexythiophene molecules, and these growth runs contain many reflectivity curves, and in total that's 376 curves. Then we can calculate the error of the neural network with respect to the manual fit, and it varies somewhere between 4% here to maybe 20%, 26% is the largest values. And on average, we are within 11% of the thickness, 18% of the roughness, and 8% of the scattering length density. So it's not quite as good as what you could achieve with a fit, but also not bad at all. And one has to stress here is that the fit sometimes needs accurate starting values to converge, whereas this one doesn't need these input values. And one could also make the neural network probably makes the predictions better if one narrows down the range where it can predict well. Where do the neural networks not predict so well? We studied this in this second paper, which has just appeared as an accepted manuscript on the webpage. Down here, neural network analysis of neutron and extra reflectivity data, pathological cases, performance, and perspectives. And I don't go too much into the detail of this paper. There are many graphs, and I don't have time to explain everything. But sort of the general results are that neural networks are quite tolerant of noise. This is also known, for example, from image recognition, where neural networks can also predict results from noisy images. So if the count rate at the total reflectivity, total reflection edge is around 1 million, we don't have any problems with the Poisson noise out here. Background scattering, for example, from incoherent scattering and neutron reflectivity is also not a big problem for the neural network if it's below 10⁻⁵. And we looked at normalization errors. If the total reflection edge is a bit 10% higher or lower than it should be, and so not normalized to 1, but maybe due to some errors we normalize a little bit off. That's also not so critical. But Noise at the total reflection edge was critical. So we really find that sensor predictions get a lot worse. The footprint correction, which also influences the critical edge, and the levels up here is also important. And for details, I have to refer to this publication that's available online now. This graph here is another one from this publication where we look at how many reflectivity curves the neural network predicts perfectly well. And one has to stress here that the network has been trained for really a huge set of a huge parameter range, ranging from negative to positive scattering length densities. And if both layers or one of them has a positive scattering length density and a reflection edge, then the performance is somewhere between 60 and 95%. However, when the total reflection edge is missing, this work shows that the accuracy of the neural network goes down a lot. The chance of predicting all parameters correct gets almost zero. Being able to make fast predictions with the neural network allows you here to study a huge parameter space and also uncover where the predictions will probably be not so good. We heard just in the previous talks that a neural network can also predict errors. We also looked a little bit at this, and in the previous talk it was called dropout of the neural network. Here I'll call it the sort of older name jackknife resampling. So just like the dropout in the neural network, we drop out if we have, for example, 8 reflectivity values, even though in reality it will be more. We just remove one of the reflectivity values and use the rest, the red points, for the fit. So we have one curve with, for example, 100 measured points. So by leaving out always one, we get 100 resampled curves, and then we do 100 neural network predictions, get out 100 thicknesses, roughnesses, and densities. And then from this distribution of the thicknesses, we can get the standard deviation of thickness, density, and roughness. And if we now look at the predicted error of the thickness, it predicts an error of here in the maximum something like 6 nanometers. And this is plotted in the space of scattering length density and the roughness. So it's a high dimensional space. So you have to look at the data in some fashion. You can choose other axes, but here we plotted 10,000 data sets and the errors thereof as a function of the scattering length density of our sample and the roughness. And we find that here for a certain scattering length density of 0.0019, we find a high error. And this is quite interesting because that's the scattering length density of our substrate. So indeed, this error estimate tells us if the film and the substrate have the same scattering length density, you have no contrast, and you cannot determine the thickness. And also, there are more complicated patterns in the roughness error or scattering length density error, where you somehow this left side here is a bit harder to predict than the right side over here. And now we can, because this is now not real data, but simulated data, we can compare it with some patterns with the true error. So see whether this resampling gives us a good indication. And indeed, it also shows the thickness error. Here, the pattern is not as clear, but over here, again, the left side is harder to predict, where we have higher errors. So the resampling is working, at least qualitatively, not quantitatively. Also notice that the scale here of the errors In reality, it's 1 nanometer, and we predict 6 nanometers. But here is a general pattern. This shape is somewhat similar. So this is work in progress, but being able to do 100 predictions for 10,000 data very quickly allows you to play with these parameter spaces to see where reflectivity has a high error or a low error. And you don't need, you can also start this with a single curve that you're interested in and predict some errors. Lastly, I want to show you some very recent work by David Maricek, where we do not predict real space as our main goal, but we predict the properties and the growth laws. And what do I mean by this? We again use our example of our growing thin film. So we have no film on a substrate here, and then we grow a film as time or exposure progresses down here, and we see these reflection fringes develop and they get narrower with time. And now we can fit each curve individually. So we have the fit parameters of substrate roughness, 80 curves where we determine thickness, roughness, and scattering length density each. So out of this data set, we can determine 241 parameters. However, these parameters are of course dependent. We know the thickness is increasing as we grow the film, and 241 parameters is not really how much information is in here. And indeed, we know a little bit about growth of layers, so we can come up with a growth model. And this growth model takes into account the critical coverage where the first layer starts to nucleate, where the second layer, the third layer, and so on starts to nucleate. So how big do the islands below have to be for another nucleus to form on top? And this can be modeled with 3 parameters, and then we model the growth rate, which can vary during growth, and the film scattering length density, and the substrate roughness. So in total, it's 6 parameters, so much easier, much smaller neural network. And we do not fit each curve individually, but we co-refine everything together in one go with the neural network. So we are doing 2 things. We are not going for the real space structure, but we are predicting parameters of a growth model, and we do everything in one go and co-refine all these curves together. And here are the results. So this is again simulated data. We hope to apply this to the experimental curve soon. The orange curve is the true simulated roughness here, and the blue curve is what our neural network predicts the roughness to be. So it's actually a pretty good prediction. And the growth model, of course, now looks smooth because we are having this model for the roughness, and it's following, especially here in the beginning, much more closely the true shape, and also the error histogram shows that the blue one, which is individual curves, has more outliers at higher coverages. So as the prediction is better with the growth model. Similarly, if we look at the thickness, again, this fluctuates if we predict individual slices, and it's perfect for the prediction from the whole image, from the co-refinement. And the error histogram also shows we have most errors below 1% for the growth model, and much more error for the individual curve prediction. So I think it's the flexibility of neural networks to predict anything you like, if you give it enough training data, makes it very enticing to go directly from data to what you really want to know, which not always is the thickness and the roughness of a film, but it can be also other properties. And I'm running out of time, so I'm just saying that we got a recent paper accepted here, where now not for X-ray curves, but for real space microscopy image, a single image is sufficient from a growth experiment to determine the binding energy and the diffusion constants, where previously you had to make Arrhenius plots and temperature-dependent laws. Now image recognition can really help to solve problems like this. So let me sum up. in conclusion, we find that the neural networks have a wider convergence range than the individual or than the current fitting tools. They have more error, but they are a lot faster. They're quite noise tolerant, but for certain pathological cases, they don't work. We can make error estimates with them. The speed really helps. And co-refinement and not predicting real space, but some other properties is also something useful. Thank you.